we were talking about vector line integrals. And remember, the motivation that led us to write down vector line integrals in the first place was this question of work, this physical quantity, this pre-existing quantity that we understand. Well, I'll say, I mean, certainly there's a very natural and powerful, and I don't want to say obvious, but the fundamental sort of a notion of physics called work. And, you write it down and compute it, and you get this thing called a vector line integral. Great. Okay. Notice, though, that assumes that the vector field that you're using in the vector line integral represents forces. Now, we know that forces are one way that you can understand, that you can model vector fields, right? They're a physical example of vector fields. But we also know that vector fields can be used to represent fluid flows. So if that's what the vector field represents, let's just say, in other words, if I take a line integral, a vector line integral, same mathematical construction of a fluid flow, what does that represent? It's certainly not work, right? There's no forces in play. So, well, then what does it represent? This is a kind of a weird question, I'll say, and what I want to give you all in some sense something to expect. What should I expect from the following discussion? And it is going to be a physical answer, right? The problem is it's not going to be a physical answer that's something that you've previously thought of, probably, or even something that I can crisply and fundamentally and basically write down and define for you, like work. I mean, work, again, it's a very fundamental physical quantity. So this is going to be a kind of a weird conversation where I'm going to make a vague description of something physical that I'd like to kind of compute, but it won't be clear exactly why or even possibly exactly what I'm computing. But the answer is going to be a vector line integral. And so the punchline of this discussion is going to be this kind of weird thing that we're going to write, this weird physical concept that we're going to write down for no apparent reason is going to be interesting because it is going to end up being the physical interpretation for vector line integrals in the context of the vector field representing fluids. So the punchline is you're going to have to kind of bear with me. I'm going to write down I'm going to start talking about a certain computation I want to do. It's going to seem weird, but just wait for it. The punchline's at the end. Okay. All right. So real quick, I wrote recall here, and really it's a recopy because in the discussion that's about to follow, I might want to have this picture and make references to certain things. So we're not going to go through that again, but this is all stuff we've seen before. Okay, so here's what we're going to talk about. We've got a curve, and I want to imagine that there's fluid all around. Of course, the fluid's flowing and such. I want to imagine that there is that I'm going to focus my attention just on the fluid that's kind of near the curve, per a cross-sectional area A indicated there. So that fluid that's kind of near in some sense, close near, but that fluid that's around the curve, it's flowing. Is it flowing along the curve? Maybe is it flowing kind of perpendicular to the curve and it just coincidentally happens to be near the curve at the moment? So to what extent, I want to ask, is the fluid flowing along the curve as opposed to across the curve? And we got to be prepared for the possibility that it might not be doing either exactly. I mean, if the fluid is doing something kind of like that, right, then to some extent, to that extent, and to at least a little bit, it flowing along the curve and also across the curve, both. But I just want to talk about the extent to which the fluid is flowing along the curve. Again, weird. Why? What's my motivation for understanding why the extent to which fluids are flowing along curves? Granted, weird. punchline at the end again. Yeah, it's not that hard of a thing to write down, really, if you think about it. I mean, here's all of my fluid that I'm interested in keeping track of, and I can look at a little bitty piece of it. There's a little bitty piece of fluid. Oh yeah, question.
Where does T come from again? I know
it's the tangent vector. Yeah, it's the unit vector pointing along the curve. That's what we call the unit tangent vector. Yep. So yeah, so there's a little piece of fluid, and as it flows, like that, the extent to which it's flowing along the curve is, well, it's the component, specifically the component in the direction of the curve, which we measure as the component in the direction of the tangent vector to the curve. So altogether then, yeah, that component times the amount of fluid, this tells you how much fluid is flowing and how much it's flowing along the curve. So altogether, for this little piece, if I want to look at just just for this piece here, the extent to which it's flowing along the curve, well, how about that? Now, again, this is not a pre-existing physical notion that we know exactly what it means, and so I'm not saying that this is should check with your pre-existing notion. We don't really have a pre-existing notion for this. I'm just saying, I don't know, I think that's a reasonable way to measure what I've loosely described here as the extent to which the fluid's flowing along the curve. Okay. Yeah, okay, so with that noted, and of course, components are easy to measure. Right, dot product with a unit vector. That's a flashback to chapter 1. This volume here is the cross-sectional area times the length ds. That's another sort of easy thing to write down. And so the little piece of the thing I'm measuring, this mysterious quantity that I'm measuring called Q, this little piece of it is computed by this formula. Which I can then add up. Let's say, well, let's add up over the whole curve. Keep in mind, there is this whole curve, and I just looked at the one little piece of it there. So adding up over the entire curve, I get this integral. And which the first thing you'll notice about it is this actually does kind of ring a bell in some sense. You see right here, integral f dot TDS. And going back up to this handily recopied bit here, that is an alternative way to write down vector line integral. All right, so I'm going to rewrite that accordingly then. This as that. Okay, so now let's rephrase what we just concluded here. I did this as a computation of the extent to which fluid is flowing along the curve, specifically fluid within this kind of, if you will, neighborhood, tube, sort of, nearbyness of the curve. And but if I want to isolate this to something that's peculiar to the curve itself, I'm going to basically divide. I'm going to say, well, let's take this area and just kind of view that as a denominator over here. And so altogether, what I'm going to get is that what the line integral represents is per unit area, of course, right? Having divided by the area, per unit area, it's representing the extent to which the fluid is flowing along the curve. So that gives us a geometric interpretation of line integrals. And so this really is the punchline. It's not that there was this physical thing and, oh, good news, we were able to compute it. There's a physical idea that we kind of hobbled together that we subsequently realize is how you interpret vector line integrals in a fluid point of view. Okay. All righty. Okay, so there is a variation of this. Anyway, sure. And that says, what if your curve is not just a random curve, but what if the curve is a closed curve, starts and ends at the same point, loops back around on itself, if you prefer. So such as let's say that curve right there, and you see it starts and ends at the same point, or you might say it's kind of a ring in some sense. Anyway. Okay, so all right, so line integral here, what does the line integral represent? Well, the line integral represents the extent to which the fluid is doing the same thing that the curve is doing. That's from above. Well, what's the curve doing? The curve is making a circle, if you will, kind of, some sense. So the line integral is measuring the extent to which the fluid is also going around in what you might call a circle. And so the line integral, with this image in mind, is sometimes called circulation, measuring the extent to which the fluid is kind of following a loop. Okay. All right. So now I emphasize this is circulation specifically when we're talking about a closed curve. So this is only for closed curves. You can't use the term circulation to represent just some random vector line integral, specifically and only for closed curves. Okay, so that in mind, looking at this case here, is there circulation around this curve, specifically that oriented curve? Yeah, absolutely. This vector field is truly following along. And if you were to measure that vector line integral, you would get a positive quantity. And so this is positive circulation, specifically positive around that closed curve. Now, here's a different curve. I know it looks like the same curve, but it's not. This is a very different curve. This is the opposite oriented curve with the same underlying, path, I guess, same underlying points. So what's the circulation here? To what extent is the vector field, you will notice it is the same vector field. To what extent is this vector field doing like this curve is doing? To what extent is the vector field kind of going around that way? Well, it's not only not, it's quite the opposite, right? The vector field, the fluid represented by the vector field is literally going the other way. And if you were to measure the line, and if you actually compute the line integral in this case, what you'd find is that you were doing various dot products of there's your dx vector, and there's your f vector, and you'd find those dot products would be negative, and you're adding that up around the entire curve, and sure enough, you would get a negative circulation there, representing that in the way that this curve goes around, the fluid is doing quite the opposite. It's going the other way. Okay, both of these examples are what I'll call geometrically convenient. In other words, the vector field is going exactly tangent to the curve. It's just, exactly along and exactly opposed in these two different cases. Sometimes, in fact, usually, almost always, in fact, it's not consistently one or the other. And so, for example, let's think about this curve here. If you were to look at that curve, is the circulation positive or negative? Well, here's the thing, kind of along in these points there, it's kind of, the fluid is kind of going clockwise, if you will. I mean, at least as pertains to this green curve, it's not going the same direction the curve is. Whereas over here on the other side, it's going counterclockwise. So this one's not immediately obvious as to whether this circulation is positive or negative. And so, so I put question mark here. And turns out there is a really good way to arbitrate questions like this, powerful way to arbitrate. And in fact, that's going to be the subject that we're going to get to in a couple of minutes. But anyway, it's not obvious one way or the other. Yeah.
So would it be different at each point?
But circulation is not defined at a point. Right, circulation is the whole line integral. Yeah, so that's what makes it hard. I mean, sure, at any given point, yeah, you get different values, but yeah, exactly. Yeah, everybody with me? So this thing called circulation is going to be an important object of interest that we're going to be doing cool things with. Okay. Oh, and I wanted to plant a thought in y'all's mind about just another way to sort of visualize, what circulation is. It's just a way to think about it. I appeal to your geometric intuition. Let's suppose I had a leaf that I'm going to represent with a disc because I'm lazy. There's a dead leaf that's been dropped in a tub of water that I have stirred. What's going to happen to that leaf? It's going to start spinning, isn't it? Right. And so just make the observation that circulation, the fact that the fluid is flowing around in a certain way, highly suggestive of which way the leaf is going to kind of rotate as it gets into the fluid represented by the vector field. So that's another way to think about circulation. Circulation is how are things rotating? If you look at a complicated flow on the surface of some big tub or whatever, it might not look like it's rotating, right? But if you drop a dead leaf onto there and it's floating, and as it's moving along, you will absolutely notice if that leaf starts to rotate as it moves. That rotation is what circulation measures. Yes.
So how does this relate to curl that we talked about?
Yeah. Long story. We're getting to it. Yep. Absolutely. Yeah. In some sense, what I'm doing right now is I'm building up to. Now, good eye, but we're currently building up to that, and it's going to take us a bit. Yeah. Yep. Okay. All right. A couple other things, though, I want to say about vector line integrals before we go on. Sometimes you get lucky. You got to capitalize on these opportunities when they come up. It saves you loads of work, and life's too hard to not capitalize on cool opportunities that arise. So here's a question that one might ask. It looks like a terribly hard question. You've got a parameterization given in spherical coordinates. Okay, that means my x is rho sine phi cosine theta. Can you imagine cosine of t squared e to the t? Yikes, right? And then y is blah, blah, z is blah, blah. I'm going to have massive amount of trig, right, in this parameterization. And on that horrifying curve, I want to compute a vector line integral, okay, which means I'm going to plug those horrifying x, y's, and z's into this vector field, and this is going to be a nightmare, right? So here's the cool opportunity to notice rho is constant, which means my curve is entirely contained on that sphere. And yeah, phi and theta are brutal. But okay, all right, let's set that aside for the moment. My curve is entirely on the surface of a sphere. The other thing to notice is, blah, blah, blah about all that business there, but our vector field is radial. Our vector field always points parallel to the position vector pointing out of the origin, which is, of course, always perpendicular to the sphere. So that's the kind of beautiful thing about it here. My my vector field is always perpendicular to the sphere. My dx is always parallel to the sphere, and therefore this dot product, f dot dx, is 0, and life is good. Right, so this is a thing of beauty. You got really lucky with the geometry here. And again, when things like this happen, don't sit there and slog through a brute force computation of that line integral. You'll pay for it with your precious time and sanity, So now I've talked to y'all before about using symmetry theorems to compute double integrals and triple integrals, and what a big fan I am, and how 20% of the integrals that I saw in my undergraduate years were zero by symmetry, and I didn't have to compute them the hard way. I don't have an actual estimate of how often stuff like this happens in physics, but it's really often. I mean, I would not be at all surprised if it was 10 or more % of the integrals that one would encounter are it just happens to, oh yeah, dot product's always, these vectors are always perpendicular, so dot product 0, we walk away. So really be on the lookout for this kind of thing. The tip-offs, the way that you notice, what should make you think to look for this in the first place are the symmetries that were evident in the statement of the problem, right? Just in a different color. The fact that rho is 1. Well, how convenient. That's an eyebrow raiser, right? I mean, that's, wow, lucky. So we're on a sphere. Spheres are great. I love spheres, right? My vector field is, am I seeing that right? It's a multiple of position. Okay, that's rare and very geometrically organized and convenient, and it just looks likely, right? In this case, everybody with me? So to try to always keep your head on a swivel and be on the lookout for again, occasionally get lucky. Okay, last thing before we go on to Green's theorem is really just a matter of notation. So we know what the dx vector is. It's x prime dt, which you can write out by coordinates like this, which you can then actually take the dt and distribute it, I guess. And then you find yourself looking at x prime dt, which of course, very naturally, you just write as dx scalar, et cetera, for the other coordinates. So what we have here is just kind of multiplying out things that we've never bothered to multiply out before. We have a different way to write the dx vector. And of course, the vector field has certain coordinates that we can give names to. And so check it out. I mean, this is just a matter of notation, but a vector line integral, if you were to actually dot out that dot, you could write like this, right? So let me erase all the rest of this stuff here. We have here an alternative notation for a vector line integral. Now, at a glance, hard to see why you'd want to do that, right? This notation over here is compact, right? And it's what I'm going to also call relatable. Relatable in the sense that this dx means something geometrically that I can draw a picture of conveniently. It's displacement. It's a physically natural thing, right? This integrand is a vector field. It's either a fluid velocity or force, or again, some physical thing. So I think this notation on the left is fantastic for the kind of things that we're going to be doing. I mean, it's compact, it's natural, hard to beat, really. Whereas by comparison, this new notation that we've got over here is not very compact. What does q dy represent? Well, long story. So it's not physically relatable particularly. You'd be forgiven for thinking this is a bad notation. So that said, it's very common, and for good reason, actually. And I just want y'all to be aware, this notation actually is very natural when you do more sophisticated math than we're going to do in this course. Our textbook, very conveniently, by the way, has a chapter on this stuff called differential forms. And roughly speaking, this is kind of suggestive. This is in the direction of what differential forms are. And there is sophisticated and substantial development necessary to be able to make good sense out of differential forms. But there is powerful stuff down that road. So I want y'all to be aware, this is not a bad notation. It's just not particularly useful for Math 219. So why am I showing you then? I'm showing you this notation because a lot of people like it for these good reasons that I just told you, and therefore you're going to see this. In engineering courses, physics courses, what have you, it's not at all rare to write things like this, and you just need to know what it means. And, you know, it's good to see where it came from. So my advice is that when you see this notation in your futures, that you think to yourself, oh, okay, the author likes differential forms. Cool, but I'm going to think of it like this. This is what he's really talking about, right? It's a vector line integral. And the PQR, yeah, that's my vector field. Is that cool? Okay. Okay, so yeah. Okay, on to section 6.2. This is a really interesting discussion. It's going to take us a little while to kind of develop up and build the ideas and put everything together, but the conclusion is shocking. This is getting into what I would call my favorite part of the course. There's a lot of ideas that are very beautiful ideas that are in the part of the course that we're sort of now getting into. So I'm going to do my best to, well, I'll say this. In writing these notes, my goal was to present the material in the way that develops the most intuition for why these things fit together in the way that they do. It's a pro-con thing. You're going to notice that what I'm about to show you is very different from what the book does. The book is much more rigorous than I'm going to be. The book proves results. This course isn't really so much about that. Right, the rigor and the proof is not really the prime focus of Math 219. So again, my presentation is going to be very different from the books. The books is lovely, but I think you'll like mine better, I hope. And I think there's a lot more intuition in mine, but I'm biased, of course. Okay, so that said, I'm going to have to develop a few ideas. First thing, I want to talk about this word boundary. Heretofore, I've been using the word boundary in a, kind of, colloquial kind of way. If you've got a fence around a region, the boundary of the region is the fence, right? I mean, it's the edge. It's where the region ends, or whatever you want to say. In particular, the boundary was not, in any sense, previously oriented. I want to now talk about boundary in a new sense. Boundaries from here on, for the rest of the course, the word boundary does not just mean a curve. It means an oriented curve. There is a specific orientation that is what I'm going to call the right orientation, or it's the conventional orientation that we pick. So anyway, the most important thing, make sure you understand this word boundary is now a loaded word. You can't say boundary, oh yeah, but I want to think of it going the other way. No, that's not what boundary means. Boundary now specifically means as follows. Here's a boundary curve. A couple of different boundary curves, I guess, in this picture. And on that boundary curve, because of the word boundary, the orientation you pick has to be the orientation such that as you walk in that direction, the region is on your left. Right now, you have to imagine yourself being on this. Let's look at the first orange curve there. As you walk in that green direction, D is on your left. Nothingness is on your right, but D is on your left. Okay, so likewise, looking at this second curve, as you walk that way, D is on your left. All right, so this is what we mean by the word boundary at this point. This is the orientation that is automatically assumed when you say the word boundary. Okay, now you may notice that this means that when you're going around the outer boundary, you're always going counterclockwise. And a lot of people like to think of the convention as counterclockwise. Problem is, it's not always counterclockwise, because not every piece of boundary is an outer boundary. And so I just point out, I mean, check it out. There is no getting around this, but the way that you would walk along this inner piece of boundary to have the region on your left is clockwise. Right, so careful with that. For what you might call inside pieces of boundary, it is not counterclockwise. So now my advice on how to think about this, some students tend to gravitate toward, okay, so in this case it's counterclockwise, in that case it's clockwise. And now you could imagine there being chunks, sort of floating chunks of solid on the inside that had little cookie cutter holes in them as well. And okay, so it's clockwise. So it alternates clockwise, counterclockwise. Don't think of it that way. It's too confusing. By far the easiest way to consistently and reliably get it correct. Always make sure you're going such that the region's on your left. That's the way to think about it. And then, look, I mean, certainly a strong majority of boundaries you're going to be looking at will also happen to be outside boundaries, in which case, yeah, okay, counterclockwise most of the time is probably going to be what happens. But when it comes time to check and make sure, the region's on your left. Okay, well, let me pause here. This is weird stuff. Is everybody with me? Yep, question?
We always take the region to be, or the D to be, or whatever on the left.
Yep, always move along the boundary in whatever direction it is that makes the region be on your left as you go in that direction. Yep. Okay, so that's again something that just has to get established. Now I've been using this sorry, question.
The boundary doesn't have to be continuous. So like,
Correct. Yeah, that's right. So this here we have sort of 3 chunks of boundary.
that's all one boundary.
This is the singular, the boundary. It's just the boundary has 3 chunks, and each chunk has a orientation you have to understand appropriately. Yeah. But the word boundary here means all together, as thought of as a single thing. Yep. Okay. Right. Okay, so yeah, next idea, and I've been using this word accumulation a lot. I've been talking about accumulating quantities, chop it up, add it up, right? Every time we write down an integral, pretty much, I talk about accumulation. And so let me just remind you, for example, I say that mass accumulates over this region. And what I mean by saying mass accumulates over the region is that the mass of that is the sum of the mass of that and the mass of that. So, you take a mass and chop it in half, and no mass disappears when you chop something in half. No mass is spontaneously generated when you chop it in half. Okay, so that's what I mean by an accumulating quantity. Mass is sort of the easy first example. I'll point out area also accumulates over areas in the sense that the area of this is equal to the area of that plus the area of that. So, no, okay. Tremendous numbers of things that we're interested in are accumulating quantities. In some sense, that's why calculus is useful, because that's what calculus is, the integrals anyway, chop it up, add it up, assumes that the quantity in question is an accumulating quantity. But not everything is actually an accumulating quantity. And I'll point out that most of the stuff, a couple of exceptions, but most of the stuff that you've computed with integrals is physical. Right, mass and work and the physical things, all the applications we talk about. But I mean, there's a few counter examples. I mean, again, area, It's not a physical thing, right? But most of the applications are physical quantities. There's a temptation to say, okay, well, physical quantities, the physical universe makes them accumulated. The physical universe is what tells us that you cannot create mass spontaneously with little fancy math games where I'm going to pretend that this is two separate regions now. Fine, but look, mass is mass, independent of your little math games, right? Okay. So it's tempting and largely correct to say that this feature of accumulation is kind of it's a feature of physical stuff. And just as to show you sort of an example, a counterexample, a perimeter is a little math concept, non-physical concept. It doesn't accumulate. The perimeter of this region is not equal to the sum of the perimeter of that region and the perimeter of that region. Right? It just isn't. I mean, this edge in some sense gets counted twice. And so the two individual pieces add up to more perimeter than the whole. So perimeter is not an accumulating quantity. Is everybody on board? Everybody see what I'm talking about? Okay. So, tempting to say that this accumulation is a mostly physical thing, and it's not even all that far off. Certainly anyway, I don't want to try to quantify that, but there are certainly some geometric quantities that are that do accumulate. And so here's the important one that we want to talk about here, boundary circulation. Amazingly, boundary circulation accumulates, by which I mean, looking at boundary circulation. If I look at the boundary circulation around the hole, there's boundary circulation around the hole. Right? And if I compare that with the boundary circulation of that piece, all right, well, the boundary circulation of that piece is like that. And then the boundary circulation of this piece right? Green plus orange is equal to blue here. In fact, here, let's see here. Let me color code. Green, okay, yeah, and then, yeah. Cool. So they do add up just like they're supposed to. And in some sense, the reason why this works and perimeter didn't is because if you look at this sort of shared edge that appears twice, it does appear twice, but it doesn't double count. If you look at those pieces, right, on the green side, you're going that way, and on the orange side, you're going that way. And they cancel. They don't reinforce and give you double the mess up, right? Double the difference, right? They just cancel and disappear in a puff of smoke. And it adds up exactly the way it's supposed to. So this is a I'm going to call this a fairly unexpected fact that the non-physical this mathematical construction called boundary circulation acts like stuff. Boundary circulation acts like a physical stuff in the same sense that you can't make mass appear or disappear by, drawing lines on a piece of paper, and you can't make work higher or lower by drawing lines on a piece of paper. Well, likewise with circulation, boundary circulation is an accumulating quantity, just like mass. So I think that's a real eyebrow raiser, and this is fundamental to how this is ultimately deep down the nugget of the point of how what we're going to eventually know as Green's theorem works. Is this fact here, is that boundary circulation accumulates. This picture here talks about how it doesn't even really matter how many pieces you chop it up into, because, so for example, I mean, if I've done a severe dicing here, right? So lots of pieces. Let me not have to, I don't want to have to ride this mess the whole way. Here we go. So yeah, but if I talk about the boundary circulation on this piece by itself, that boundary circulation is that. Now, by the way, notice I'm following the orientation rule. The region's on my left as I go around that boundary, or, you know, again, loosely, casually, counterclockwise, right? But then now over on this piece here, same deal, going counterclockwise, regions on my left. And notice the same exact phenomenon happens. This edge appears twice, but with opposite orientations. They cancel, it disappears in a puff of smoke. It never happened, right? And then it likewise for all the other interior edges. This edge is part of the boundaries of two of the chunks that I've chopped it up into. Always opposite orientations. They cancel, disappear in a puff of smoke. So does that one and that one and that one and that one and that one. They all just disappear. All these shared interior edges. This is going to take too long. I got myself in trouble here. There we go. Those all disappear. The only pieces of boundary circulation that don't disappear are the ones for which there is no other side to cancel with, namely the outside edge, namely the boundary circulation of the whole in the first place. So boundary circulation accumulates any which way you slice it. Okay, so anyway, neat fact. Again, very fundamental. Just a little bit of foreshadowing. We are eventually, so this is, we're working right now in the section called Green's theorem. We're building up to Green's theorem, which we'll hit in just a couple of seconds here. Before we're done today, I'm gonna be able to write down Green's theorem. But heads up, we will also, and I think you know this, eventually be talking about the divergence theorem and the curl theorem, otherwise known as Gauss's theorem and Stokes's theorem. Those are going to be a big deal as well in this course. And this idea of cancellation, this idea of accumulation is the big point for those theorems as well. Just in different ways, they're about different kinds of geometric objects, but morally, it's the same kind of deal. Okay, so that's why I'm being real careful with this. Okay, so let's talk about density. Old concept. If you have mass distributed in some way, where there's, you know, maybe more mass over here and maybe less mass elsewhere, however the mass might be distributed, density says, well, look at a small region and talk about how much mass there is in that region. And then, you know, then you of course have to know the area of the region as well. And so, you know, mass divided by area is density. Mass divided by area. This notion of density is, you might say, the thing that you multiply by area to get mass. This is the thing that you put into an integral, is mass per unit area. Now I want to say that a little bit differently. I can talk about how much mass there is in this region because mass is an accumulating quantity, right? It's specifically because I got all this mass in my initial region, and because it's an accumulating quantity, I can chop it up however I want and specifically isolate the mass that is literally in that little region. Okay, well, circulation is an accumulating quantity too, right? So I might be interested in, let me go back up to this picture here. I might be, oh man, I made a mess. Note to self, don't do that one again. Okay. I might be interested in the circulation around the whole of whatever this this region is, right? But I can ask, it seems weird, but I can ask how much of that circulation is happening in this region here. And the temptation is to say, well, that circulation's happening on the boundary. It's not happening in the interior. Well, actually kind of is, right? Because it's an accumulating quantity. We've established that. I can chop it up however I like. The sum is the adds up to the whole. So I can talk about how much of this purple circulation is actually happening in that little green box. And so along those lines, circulation, you can talk about how much circulation is happening in there. It's computed exactly like you would think. You just take that little circulation around that outer boundary. You divide by the area. That gives you circulation per unit area. That's the thing that you multiply by area to get circulation. That's going to be the integrand in your ensuing integral when you're trying to compute circulation. Just like with mass. And here's where I'm going to sweep something under the rug. And this is just details, really. It's not a hard calculation to do. It's just a tedious, well, it's the wrong word. It takes a little bit of time that I don't, like if this was a full year class, I would totally do it. Right. But we're in a semester, we're in a hurry. So if you want to see the calculation, go to the book. It's in there. It's great. But this density, this boundary circulation per unit area, what I like to call, and most people call circulation density. There's the formula for it. dq dx minus dp dy. Nice little formula. So this goes by many names, many notations anyway. I like to call it Green's operator because it's the operator that shows up in Green's theorem. I like to denote it GRN as a compact and convenient sort of a compression abbreviation of the name Green. So to me, that makes sense. Some people call it the rotation of the vector field. Some people call it the curl of the vector field. And then the book introduces this notation over here that I actually really don't like. But in the interest of time, I won't complain about why I don't like it, but you can write it like this because the book does. But this thing, give me 2 seconds. This thing is, I mean, let's talk about these terms down here, rotation and curl. If you look at where it comes from, what it's measuring is literally circulation. It's measuring the extent to which the vector field is kind of following along that boundary. It's literally measuring how much the vector field is kind of rotating, curling, you might say, around that region per unit area, right? So it is literally circulation per unit area, and thus these names down here, rotation and curl. Yes, you had a question.
Yeah, I was asking if the Green's operator and the curl are the same thing as the circulation density.
Yeah. These are all this. Yeah, that's right. So let me again with the colors. Okay, so circulation density, circulation per unit area, Green's operator, Green F, Rho F, curl F, and this notation I don't care for. Those are all referring to the same thing. Yeah, exactly. So again, the connection that I'm leaving off, and apologies, but we're in a hurry. The actual computation that this intuitive concept of circulation density is computed by this algebraic formula is details. Don't sweat it. Okay. All right. So we are basically done with Green's theorem. We've already, in some sense, proved Green's theorem. Let me just observe. This isn't a proof. This is an observation that we've already talked about how boundary line integrals represent circulation. We've made the observation that circulation accumulates over its interior. Now literally, that's all this says. The total circulation is the sum of a bunch of little pieces of circulation. In the same way that mass is the sum of a bunch of little pieces of mass, this is the accumulation feature that we established. And then above, we noted that the circulation per unit area is that formula. It goes by many names. I like to call it Green's operator. You can call it curl or rote or whatever you want to, but anyway, it's Green's operator. And so done. This is Green's theorem. Green's theorem says that circulation, boundary circulation, is computed by a particular double integral over the region whose boundary is that closed curve. So said differently, line integrals can be computed with double integrals. Vice versa, if you prefer, but most of the time we tend to do that. Okay, that's a good stopping point, and we're out of time. So see y'all later, and yeah, have a good one. See you on Friday. Oh, some of y'all may have come in after I started.